We'll continue our discussion talking about the physical properties of alkanes. When we talk about physical properties of a compound, we're usually talking about stuff such as melting point, boiling point, density, or solubility. Alkanes are overall nonpolar. They're made up of only carbon and carbon-hydrogen bonds have a difference in electronegativity of about 0. So since they're nonpolar, they will be soluble in other nonpolar stuff. Remember, likes dissolve likes. When comparing their either melting point or boiling point, depending upon if they are a solid or a liquid, we want to look at the amount of London dispersion forces that would be present. And the greater the number of electrons, or the higher the molecular weight, the more London dispersion forces that will be present. So we can compare something like N-pentane, which stands for normal pentane, meaning it's just a straight chain, to N-butane. Pentane has the chemical formula C5H12, whereas butane has the chemical formula C4H10. Remember, you can figure out the chemical formula for any alkane using the generic formula CnH2n plus 2. So if we look at the boiling point for pentane is around 36 degrees Celsius, whereas the boiling point for butane is -1 degree Celsius. This tells us that at room temperature, pentane is a liquid, whereas something like butane would be a gas. So pentane has greater London dispersion forces than butane does. It has weaker London dispersion forces when comparing it to pentane. Pentane has more electrons and more opportunity for movement of those electrons, which leads to the greater London dispersion forces. The greater London dispersion forces lead to a higher boiling point. The properties of alkanes can change depending upon how they're branched as well. So branched chains have a more spherical surface than a straight chain, and therefore the branching creates a lower surface area when compared to a straight chain. So here we can compare something like butane to isobutane, which is an isomer. Both of these have the same formula, C4H10. So they have the exact same number of electrons and the exact same number of carbon and hydrogen atoms, but they have very different boiling points. Butane, as we just saw, has a boiling point of -1 degree Celsius, whereas isobutane has a boiling point of -12 degrees Celsius. So our butane has greater London dispersion forces than our isobutane, which has lesser London dispersion forces. The straight chain has higher dispersion forces because it has a greater surface area. And this leads to the higher boiling point that's seen. Later, we'll see that a really important part of studying organic chemistry is learning the types of reactions that certain classes of molecules undergo. Alkanes are the least reactive type of organic compounds, and we don't really have any reactions to study for them. The type of reaction that they usually undergo is combustion, which we would have talked about briefly in general chemistry. A combustion reaction is a hydrocarbon plus oxygen reacting to form carbon dioxide and water. So in this example, we have methane, which is CH4, reacting with oxygen, diatomic, it's O2, and then forming CO2 and water. Notice our reaction isn't balanced as written. We have 4 hydrogens on the left and only 2 on the right. So we actually would have to put a 2 out in front of our water. That would give us 4 hydrogens now. And now we have 4 oxygen atoms on the right-hand side. So we would also need a 2 out in front of our O2 as well. You should be able to write the combustion reaction and balance it for any given alkane. Alkanes contain all single bonds, and those single bonds can rotate in space. The different ways that we can rotate the bonds are called conformations, or conformers. We're going to spend a good chunk of the rest of this learning different ways to draw Newman projections, which is one way to represent the conformations of alkanes. So we briefly talked about wedge and dash notation, where the wedge means that it's coming out at you, so it's coming out away from the paper, and then a dash is pointing backwards. Sawhorse projection is kind of similar to a Newman projection, but the Newman projection is like a flattened version of that Sawhorse projection. So if these three blue hydrogens are in the back, that's where they are at on this Newman projection. And then we have the three red hydrogens in the front, and that's where these three are on our Newman projection. So it's like we're looking straight down at it, whereas on the Sawhorse projection, we're looking at it from an angle. So this would be a carbon here. This would be a carbon here. And then there is a bond attaching these two carbons together. We don't see that bond on the Newman projection. That's what these circles represent, are the front and back carbons. So we're not seeing this bond right here. So a Newman projection is a type of a planar projection. It's along a certain bond, and usually that bond has to be identified. It's called the projected bond, that one that you're not seeing. And the conformations are interconvertible, and some are more stable and some are less stable. The stability of a certain conformation will depend upon a few different types of strain. So we're going to look at the definitions of what those mean. The first thing is torsional strain. This is the repulsion between electron clouds when they are forced into close proximity of one another. There is also steric strain. This is a repulsive interaction that occurs when large atoms and groups are forced close together, more so than their atomic radii will allow. And another term that we'll often use when talking about Newman projections is called the dihedral angle. Sometimes it's called the torsional angle, and it's represented with lowercase Greek theta. And this is the angle between the two planes. So there are some dihedral angles that are favored, which lead to lesser steric strain, lesser torsional strain, and a more stable conformation. How you draw a Newman projection is that you're imagining that you're looking directly down a carbon-carbon bond. And off of that carbon, there's three other things that are attached. The bond you're looking down is that projected bond that we don't draw. And then on the carbon on the back end, there's three things attached. So we want to show this using a Newman projection. And we draw a dot in the front, and we represent with that dot the three atoms that are coming off of the front carbon. So in this case, all three of them are hydrogen, represented in red. And then we draw a circle behind it to represent the back carbon. And that back carbon in this example has three atoms coming off of it, and they are our blue hydrogens. Now, there are different ways to draw Newman projections, and this is just one way how we have all of the atoms staggered out so they're not lying on top of one another. And we'll see in a second that this is just one conformation of how the hydrogen atoms could be when we compare the front to the back. So when we look at ethane, which ethane is C2H6, we have a molecule that has a carbon and another carbon, and then coming off of there we have three hydrogens on the front, and then we have three hydrogens on the back. And so if we imagine that we're looking at this, we would be looking down this carbon-carbon bond right here. That's the one we wouldn't see. And so this is a really simple molecule, but usually it's helpful to list what atoms are coming off of each of your carbons. So if we call the first carbon C1 and the second carbon C2, we can say what we have specifically coming off of them. So C1 has hydrogen, hydrogen, and hydrogen, and C2 has hydrogen, hydrogen, and hydrogen. So there's three hydrogens coming off of each carbon. Later we'll have to prioritize who is essentially bigger and bulkier and who it should be across in order to draw the lowest energy or the most stable conformation. But since all of them are hydrogen right now, we can essentially place them anywhere. There's two important conformations to know about: the staggered conformation and the eclipsed conformation. The staggered conformation is where everything is spread out, and this is going to be the lowest energy conformation. When we say lowest energy, that means most stable. So this is how the molecule would like to arrange itself. The eclipsed conformation, if you think about what an eclipse is, that's when it's covering up. So this is how we show it covering up when we're drawing it on paper, but you can imagine that everything would be on top of each other. This is going to be the highest energy conformation, or in other words, the least stable. And so for something like ethane, that's pretty simple. Now we can just place our hydrogens. So this is our front carbon, and this circle represents our back carbon. And so coming off of our front carbon, we have hydrogen, hydrogen, and hydrogen. And then coming off of our back carbon, in red, we have hydrogen, hydrogen, and hydrogen. So in our staggered conformation, if we were to think about what is the dihedral angle between a back carbon's hydrogen and a front carbon's hydrogen, here theta would be equal to 60 degrees. Between any back hydrogen and any front hydrogen, those are going to all be 60 degrees apart. So in the staggered conformation, that's the farthest they can space themselves out, and so this is going to be our most stable Newman projection. For our eclipsed conformation, our front carbon has our 3 hydrogens coming off, and then our back carbon, we have our 3 hydrogens here, and we can't show them directly on top of each other on 2D paper, but in this scenario, theta, or our dihedral angle, would actually be equal to 0 degrees, because they would be perfectly aligned if we were looking at this in 3D. So this is our least stable conformation, because having that dihedral angle of 0 is going to cause some types of steric strain and torsional strain by having those electron clouds and atoms in close proximity to one another. So it's less favorable to be in an eclipsed position. So as we saw in the previous slide, some conformations are higher in energy and they are less stable, and some conformations are lower in energy and they are more stable. And there are a ton of conformations. So if you imagine you take your front carbon and you can spin those 3 hydrogen atoms 360 degrees, and then you take that back carbon and you could spin the back ones 360 degrees, that for any projected bond that you're looking down, that means that there's a total of 720 possible conformations. Now, most of them are unimportant. The ones we're going to focus on primarily are the staggered conformation, which is the lowest energy, and the eclipsed conformation, which is the highest energy. So that dihedral angle is the angle between the atoms on adjacent carbons, essentially. In this case, we're looking at hydrogen atoms because we're still talking about ethane. So this would represent dihedral angle of 60 here. We're looking at one that's on the front and one that's on the back carbon when we're looking down that projected bond. When different atoms are lying on top of each other and they have torsional and steric strain in that eclipsed position, the sizes of the atoms will matter to determine how much energy is essentially produced from them being in that unfavorable eclipsed position. So the difference between where we have our hydrogen atoms separated from one another as far as they can be versus anywhere where we have 2 hydrogen atoms on top of each other. So essentially the difference between our staggered and our eclipsed. Whenever we have 2 hydrogen atoms lying on top of each other, that's a potential energy gain of 12 kilojoules per mole. Now this isn't a number you need to memorize or anything, but we'll see that hydrogen's a really small atom. And so when we have 2 hydrogens essentially on top of each other, it's not that huge of an energy gain. As the group gets bigger and bigger that's being eclipsed, the energy gain will be more and more and more. Now that we looked at ethane, let's build up and look at propane. So propane is going to be C3H8. So if we draw this out longhand, we'd have 3 carbons, and coming off of one of the carbons, we're going to have 3 hydrogens. Coming off of the middle carbon, we're going to have 2 hydrogens, and then coming off of the end carbon, we're going to have 3 more hydrogens. So let's say that our projected bond, the bond we're going to look down, is C1 to C2. We could say C2 to C3 as well, and it would be the same because it would be the mirror image. But in this case now, we've introduced some differences. So between C1 and C2, everything coming off of C1 that is not C2 is going to be 3 hydrogens. So here is our 3 hydrogen atoms that are coming off of C1. We're imagining that we're looking down the bond, so that would be where our I is at. And this is going to be our projected bond, C1 to C2. So coming off of C2, everything coming off of C2 that's not C1, we've got a hydrogen, and then we have this whole CH3 group. So we've got hydrogen, and CH3. That group is called a methyl group. Not methane because it's not the parent of the molecule, but methyl because it is a CH3 group coming off of the chain. So now we have something other than hydrogen. So when we place our first 3 atoms, so imagine this is our C1, and we've got hydrogen around C1 in all locations. And then when we put our atoms on the back, it really doesn't matter where we place them because no matter what we put down back there, everything's going to be across from a hydrogen. So hydrogen, and then I'll just place our methyl group or our CH3 at the bottom here. But notice wherever I had placed it, it wouldn't have mattered because it's going to be across from a hydrogen everywhere. So in this case, we have our dihedral angle, which is going to be 60 degrees if we're looking at the angle between a front hydrogen and a back hydrogen. And in this case, we have a dihedral angle of 60 when we're looking at a front hydrogen and our back methyl group as well. For the eclipsed conformation, we're going to have our front 3 hydrogens, and then our back atoms, we're going to have hydrogen, our methyl, and our hydrogen. And so it's hard to tell with the drawing, but our theta, or our dihedral angle here, is 0 degrees for all of these. That's what eclipsed is, where you have that dihedral angle of 0. So this would be our lowest energy, not lost, lowest, the staggered conformation, and the eclipsed would be our highest energy, or our least favored conformation when we draw propane. So if you recall the potential energy diagram that we just looked at for ethane, now we can compare that to propane. So at the top up here we have our eclipsed conformation, and at the bottom this would be a staggered. And so our eclipsed is our high energy conformation that's less favored. With ethane, we had 2 hydrogens on top of each other, and that showed an increase in potential energy of 12 kilojoules per mole. Here we have a hydrogen eclipsing with a methyl group, and that methyl group is bigger and bulkier than just another hydrogen was. And so notice that the potential energy gain is now 14 kilojoules per mole, so that we see a larger increase in potential energy when going from the staggered to the eclipsed position or conformation for propane, because now we have a hydrogen methyl interaction. So the bigger and bulkier that group gets that's overlapping with another group, the greater the potential energy gain is going to be, and the less stable that conformation will get. Next, let's analyze what our Newman projections for something like butane would look like. We're going to pretend that we're looking down the C2 to C3 bond. That's going to be our projected bond. So if we number this, we would have 1, 2, 3, 4. And we're going to be looking down here from 2 to 3. So when we list what is on carbon number 2, coming off of carbon number 2, we have a methyl group, a CH3 group, which would be carbon number 1, and we also have 2 hydrogens coming off. So we have methyl, and we have hydrogen and hydrogen. And then coming off of carbon number 3, we have another methyl group, or CH3 group, and then we also have 2 hydrogens coming off of there as well. So we're not looking backwards to C2 because that's our projected bond. So now we have a situation where we have 2 bigger groups, the 2 methyl groups, one coming off the front and one coming off the back. So there's multiple ways that we could draw the conformation of butane looking down that C2 to C3 bond. So on our front carbon, which is this one in the middle here, we're going to list what we have coming off of there, and I'm just going to put the methyl group, which the abbreviation for methyl is just Me, off the top, and then the hydrogens on the left and right. It doesn't really matter where I put them yet, but when I show this first conformation, which is called anti, the anti-conformation is where we end up having a 180-degree torsional angle between the front carbon's largest group, which is methyl, and the back carbon's largest group, which is also methyl. So the other methyl is going to go pointed down on that back carbon. So remember that circle is showing the back one. And so then the other 2 are just hydrogens there. But what we have here in this anti-conformation is a dihedral angle equal to 180 degrees. So in this situation, the 2 biggest, bulkiest groups, which are the 2 methyl groups, are the farthest apart that they can be. So this would represent our lowest energy conformation, or in other words, our most stable. So this is the best situation for our conformation of butane, for it to be at the lowest energy. And this is a staggered conformation. Notice that when we're looking at the angles between any of the given front and back ones, they are 60 degrees apart. So for example, in between these 2 hydrogens, that's 60 degrees. And between this methyl and this hydrogen, that's 60 degrees. So this is still a staggered conformation, but it's called anti because of those 2 methyl groups being 180 degrees apart. And then the next 2 are called gauche, and they are also staggered conformations. So all 3 of these represent a staggered conformation. And when we have a gauche interaction, that's where our methyl groups are, they're still on the front and they're still on the back, and the molecule is staggered, but now they're next to each other. So if our front carbon had a methyl group there, and then we had the 2 hydrogens there, now imagine instead of the methyl group being 180 degrees apart, that maybe the methyl group is 60 degrees apart. So here we have a gauche interaction. Theta, the dihedral angle between the 2 largest groups, is equal to 60 degrees here. And the other gauche interaction would kind of be like the mirror image of this. We would still have 2 methyl groups having a dihedral angle of 60 degrees, but instead it would be on the other side. So keeping everything else the same, but moving that methyl to the other side here, still representing a dihedral angle of 60 degrees. So that's gauche, where you have them next to each other, but they're not in the eclipsed position. They're next to each other, but they're staggered. So this isn't as low of energy as the anti-staggered conformation would be, but it's better than the eclipsed. So the eclipsed is our highest energy, least stable conformation, where now we're going to have a situation where our hydrogens and our methyls, our 2 largest groups, our methyls, are on top of each other essentially. And this is how we show them being on top of each other. We've kind of rotated it so it looks like they're not staggered. Our theta here, the dihedral angle, even though we can't tell how it's drawn, is essentially 0 degrees. And this represents our highest energy, which is our least stable conformation that we could draw. Out of all the possible conformations, the eclipsed conformation with those 2 methyl groups on top of each other is the least stable one for butane. So this picture shows exactly what we were just looking at with the Newman projections, but it's a little bit easier to see how bulky the methyl group could be. Even though methyl is actually a relatively small group, it still can interfere with one another, especially when it's in that gauche positioning. So notice in the anti-staggered conformation, there's that 180-degree dihedral angle between the 2 large largest methyl groups. They're the farthest apart that they can be. That's why that's the most stable conformation. And then the two gauche interactions, they have that 60-degree dihedral angle, and you can see they're actually overlapping one another, regardless of what side they're on. So those methyl groups are having a bit of strain when they're in that gauche arrangement in that dihedral angle of 60 degrees. So it's not as bad as it would be for the eclipse, but they still are having interactions, and they can have steric strain and they can have torsional strain. And if we analyze the potential energy diagram for butane, looking down the C2-C3 bond, we can see we have some of our eclipsed conformations that could be possible, and we have some of our staggered conformations that could be possible. With the staggered conformations always being lower in energy than all of the possible eclipsed conformations. So notice that at energy height, that's our maximum there, 19 kilojoules per mole. That represents our least stable arrangement, or least stable Newman projection, where those two methyl groups are directly on top of each other. Next to that, we have a conformation that we didn't draw on the previous page. We have an interaction here. It's a eclipsed conformation, but we have a hydrogen on top of a methyl and a hydrogen on top of a methyl. Those two are going to interact as well, just because methyl is much more bulkier than some of the other things. So that still creates an energy increase of 16 kilojoules per mole, just not as much as when the two methyl groups are on top of each other. And down below for all of the staggered conformations, so our lowest energy is going to be the anti, where the methyl groups are 180 degrees apart. That's the best we can have. And then the next best would be the two gauche interactions, where the methyl groups have a dihedral angle of 60 degrees. So that gives us a much smaller energy increase of 3.8 kilojoules per mole. So staggered is always better than eclipsed in terms of being more stable. Let's practice drawing a couple Newman projections for the given molecule down the projected bond that's indicated. And let's draw the most stable and the least stable conformation, and then essentially we could say why that is. So if this is our first carbon, let's call that carbon 2, and then the next one would be 3, and then we have 4 total, so this is going to be a derivative of butane. If we were going to name this, we would call it 2,3 dibromo butane. And don't worry about the wedges for now. I mean, the wedges do mean that they're coming out at you, but we will study a whole chapter on stereochemistry a little bit later in the class, where we learn how to pull apart the differences between wedges and dashes and how we determine those orientations and whatnot. So for now, let's just say what's on carbon 2 and what's on carbon 3. So coming off of C2, we have a methyl group, we have a bromo group, and we also have, what's not written, a hydrogen. And since this molecule, if you notice, is actually totally symmetrical, coming off of C3, we actually have the exact same things. We have a methyl group, that's our methyl group right there. We have another bromo group, and then that's not written, we have a hydrogen. So when we start drawing our Newman projections, we're going to start with drawing the front carbon, and then those 3 bonds would be coming off the front, and then the circle, and then we have the 3 coming off our back. So this would be a kind of a layout that you would draw for when you're drawing your staggered conformation. Now, when we do our staggered conformation, the one we care about the most is the most stable, lowest energy one. So in order for us to draw that one, we want to think about how we're going to orient the 3 things on the front and the 3 things on the back. So on the front, in order to keep this lowest energy, my 2 biggest groups are methyl. I should put those 180 degrees apart from one another. So my front methyl should go above my back methyl and keeping those at 180 degrees, since those are the largest, bulkiest groups in this example. Then next, I should probably keep my bromo groups 180 degrees apart from each other as well, because those are my next biggest thing that I'm gonna have to worry about. So my front one, I'm gonna put here, I have a bromo, and that's gonna be across from another bromo group. And then lastly, the smallest atom is hydrogen. And so in our most stable conformation, hydrogen would end up being across from one another. So my back hydrogen there across from my front hydrogen here. And so this represents our lowest energy, or in other words, most stable conformation, which is our staggered version of it. We have 180 degrees between the largest groups in all of them, and the dihedral angle in each case, theta, is 60 degrees. And then next we want to show the other important conformation, which is our eclipsed conformation. So when you're starting to draw your eclipsed, you can start it off the same, show your front carbon of the projected bond, and then your circle that represents the bonds coming off of your back carbon, but you're going to keep them close together. So you're going to have one here, one here, one here. That's us trying to show that they're essentially lying on top of each other. They're overlapped. And when we are showing our eclipsed conformation, now we want to have the highest energy, least stable molecule. So in this scenario, we'd want our two biggest groups lying on top of each other. So methyl group on the front would be right next to the bulky methyl group on the back, because that's the worst. Same thing with the bromos. We're going to have the bromo group on the front carbon right next to the bromo group from the back, and then the hydrogen on the front would end up being next to the hydrogen on the back. And that's just how it all ends up falling when we have to write it for the eclipsed one, because the two methyl groups would dictate being next to each other because they're the biggest, and then the two bromo groups would have to be next to each other. Our dihedral angle here for an eclipsed is 0 degrees, and this would be our highest energy conformation. So it's important to be able to always draw at least the highest energy and the lowest energy. Those are going to be the most important ones. And then analyze them. What are the dihedral angles in them? What is going on? Why is one group across from the other? Or why is one group next to each other? Let's try another example. First, let's name the molecule. So this is a carbon at the end here. This would be a CH3 group. And when we start numbering, I'm going to start numbering from that side, so my substituent has the lowest number possible. So 1, 2, 3, 4. So naming this, we would have 2-chloro, and then we have 4 carbons, so we're going to have butane. Chloro is our only substituent at position number 2. Like I said, don't worry about the dash right now. That's just showing us that our methyl group is pointed back into the plane. So we're looking down C3 to C2, essentially. And so our groups coming off of C3, we have 2 hydrogens right here, and we have a methyl group. So we have methyl, hydrogen, hydrogen. And then our groups coming off of C2 are, we have a methyl group, CH3, we have a chloro group, and then lastly, what's not shown, the 4th bond on carbon, is hydrogen. So when we prioritize these, the largest, bulkiest groups here are methyl, just that CH3 group. The next biggest one would be chloro, and then the smallest would be hydrogen atom. So let's show our staggered and our eclipsed conformations, our least stable and our most stable. So here's our staggered one, and our staggered conformation off the front, we're going to have methyl, and we're going to have hydrogen and hydrogen, so just placing those there. For our staggered, our lowest energy one, we are going to put the other methyl group 180 degrees apart, and then we have to throw a hydrogen on there, and then we have to put the other chloro group on there. So this would represent our lowest energy, aka our most stable Newman projection. Next, let's draw our eclipsed. So starting off the same here, we're going to put these other ones, the back ones, right next to the front ones. We can put our front ones in the exact same spot to start with: methyl, hydrogen, hydrogen. And now for our atoms or our groups coming off of our back carbon, our methyl is going to go next to our other methyl. there's going to be a chlorohydrogen interaction, and then there's going to be a hydrogen-hydrogen interaction. And there's an energy that's gained when going to this higher energy conformation for all of those groups overlapping. Some are just more significant energy gains than others, such as the methyl-methyl interaction. That's a bigger increase in the potential energy than the hydrogen-hydrogen interaction. So we have our dihedral angle of 60 degrees here, and in the eclipse, we have our dihedral angle of 0 degrees. And so this would be our highest energy or least stable conformation. Next, let's take this Newman projection and transform it into a line bond structure so that we can give it a proper systematic name. So this is an important skill to be able to have as well as to work backwards. So how I would start is look at your front carbon. We're not going to do any numbering just yet. We're going to look at what groups are coming off of our front carbon. So notice off of your carbon here, you've got 1, 2. So that's a 2 carbon substituent. That's called an ethyl group. Right here, you have 1, 2, 3. You have another substituent. This is a propyl. And then coming off the top, you have 1, 2, 3. So you have another propyl group. And that's all off of the front carbon. So 2 propyls and an ethyl group. Coming off of the back carbon, here we have 1, 2, 3, 4. So that's a 4 carbon group. And notice it's not attached at the second position. This is called isobutyl. When the 4 carbons are in that arrangement, it's an isomer of butane. So similar to, we have isobutyl, sec-butyl, tert-butyl. This arrangement is the isobutyl. It's similar to isopropyl, only it has 4 carbons. And then we have a bromo group. And then this one right here, which maybe we should pull this out and just kind of look at that separately. So there's where it would be attached. This doesn't have a common name. This is going to be something that has sub-branching that we would need to name because we have a halogen coming off of a certain number of carbons there. So this would be 1', 2'. So we're going to have 1' chloro. And then since there's a total of 2 carbons in that little sub-branch right there, this is going to be ethyl. So that's the name of that specific sub-branch, 1' chloroethyl. So we'll have to figure out what carbon that's actually coming off of on the back once we get a proper numbering scheme done. So now that we know what the 3 groups on the front are and the 3 groups are on the back, we can kind of make a sketch. And it might not be pretty at first, but we can use it to then draw a better line bond structure to help us name this guy. So this is going to represent my projected bond. That's my bond that is in the front, and then that's my one that's in the back. So what are my 3 things coming off the front? We said we had an ethyl, and we had a propyl, and we had another propyl. So 1, 2, 3 for each of those propyls. And then we'll draw the 3 things coming off of the back carbon. So off of our back carbon, we had a bromo group, we had an isobutyl group, and then we had our sub-branch, which was our 1' chloroethyl. So this doesn't look like a nice, neat line bond structure, but we can name it from this. And if we wanted to, we could redraw it with proper angle conformations and kind of showing it, you know, in that nice, neat way that we're used to seeing them. But what we really need to first do now is just identify the longest carbon chain. So now that we have everything drawn out, we're going to kind of look and count and see where we would start numbering from and pull together our longest carbon chain. So we could go 1, 2, 3, 4, 5, 6, 7, 8.
So it looks like we're going to have 8 carbons in our longest chain. And if I start numbering from the right, I hit my first substituent at position number 2, and then my next substituent at position 4. If I had started numbering from the left, I would have had 1, 2, 3, 4. So I would have gotten to 4 before I came upon that ethyl and propyl group. So we're going to go with the lowest numbering possible. So we're going to start with the numbering scheme that's in the red, starting from the right here. So making a list then, we had 8 carbons, so this is going to be octane. And then we had 2 methyl. We had 4 bromo. We had a 4 subbranch, which is going to be 4 parenthesis 1 prime chloro ethyl close parenthesis. Notice there's no hyphen in between the 4 and the parenthesis because we don't have to separate those two numbers with a hyphen in between them because the parentheses there indicating that that's where that subbranch lives. We have a 5 ethyl. And then coming off of number 5, we also have a propyl group. So those are all of our substituents on our octane chain. So now we just need to put them in alphabetical order when listing them in the full systematic name. So what's going to come first? Alphabetically, we're going to have B for bromo, and then C for chloro, E for ethyl, M for methyl, and then P for propyl last. So we're going to have 4 bromo, 4 1 prime chloro ethyl, close your parenthesis. We're going to have 5 ethyl, 2 methyl, 5 propyl, octane. And let's do one more Newman projection example. We're going to draw the projection about the C3-C4 bond for 3-methylhexane, and we're going to show the highest energy conformation and the lowest energy conformation. So first you want to start off by actually drawing your molecule. So hexane is 6 carbons in the parent. And then at position number 3, we have a methyl group coming off. And we are looking down the C3-C4 bond. So that's our projected bond. That's where our eye is looking. So coming off of position number 3 and then coming off of position number 4, we want to list what groups we have. At position number 3, we have an ethyl group, a 2-carbon chain. It's going to be the largest one. So I tend to kind of list them in order, either putting my largest on the top and then working way down to my smallest, or vice versa, just so that I know. At position 3 next, we have a methyl group. That's a little bit smaller than the ethyl. It only has 1 carbon. And then unshown is a hydrogen. Coming off of the back carbon, C4, we've got another ethyl group. And then unwritten, 2 hydrogens. So hydrogen and hydrogen. So this helps us when we go to place them on our staggered and our eclipsed conformations, because now we have them written in order, so we can just glance at the list a little easier. So starting off, we're going to draw our lowest energy conformation. Which is our staggered. And in this one, if we want it to be lowest energy, that means most stable, we want to put our 2 bulky ethyl groups as far apart as they can be. So the front carbon's ethyl has to be across from the back carbon's ethyl. Those are anti to one another. And then on the front carbon, we have a methyl and we have a hydrogen. Well, because on the back carbon, there's just 2 other hydrogens, it doesn't matter where I put those, because it's going to be hydrogen across from the methyl and hydrogen across from the other hydrogen. But what's important is that my 2 bulkiest ethyl groups have a dihedral angle of 180 degrees there. But everything between front and back has a dihedral angle of 60 degrees. For our eclipsed conformation, we have our front carbon, we have our back carbon. We can start by putting our ethyl group on there on the front, our methyl group on the front, and our hydrogen. And when we have our highest energy conformation, those two ethyl groups, front and back, are going to be right on top of each other with a dihedral angle of 0. Same thing for everything else. The hydrogen is going to be with another hydrogen, and the methyl is going to have to be paired up with another hydrogen. So this would represent our highest energy conformation.